Hi guys, Miss Fitable here, bringing you a screencastify presentation on the emission spectrum for hydrogen atom. And I love this so much because we're going to get to talk a little physics. So we won't do a lot of quantifying in this lesson, but we will be using our reference table, in particular page 8. On the bottom where there is a model here of the energy levels of a hydrogen atom. So we've learned about models of the atom. We learned about the Bohr model for the atom, in which the nucleus in the middle here consists of protons and neutrons. And around the outside, you have possible energy levels where the electrons are held. And in the Bohr model, I'll go to my next slide here. In the Bohr model, the electrons have to exist in discrete energy levels, which just means that they have to be in specific locations. An electron can't be halfway, between one of these energy levels. It's either in the energy level or it's not, or it's in the next energy level, or it's in the next. So they designate these energy levels as n equal 1. That's the energy level that's closest to the nucleus. N equal 2 is much further out. N equal 3, a little bit further out. N equal 4, a little bit further out. And it goes all the way out. In this image, it goes out to N equals 6. So those are the possible energy levels. And today we're going to get into proof that these energy levels actually existed, because before Bohr came along with this model of the atom that has these energy levels for electrons, all we had was Rutherford's model. And Rutherford knew about the nucleus, but he had no idea what the electrons were doing. So, so let's get into it a little bit. Okay, so first of all, can the electrons jump around in these energy levels? And the answer is absolutely. In order for them to jump around, they have to absorb some energy from some type of source. So if I had a sample of hydrogen gas and I electrify it somehow, I'm giving those atoms some energy, then the electrons can jump from lower energy levels out to higher energy levels. And then we say that the atom is excited. So we're going to look at a little simulation of how that happens. A little bit of a problem is it doesn't last. So you can jump electrons out to higher energy levels, but they won't stay there. They will drop back down to their lower energy level. And it's called the ground state, the lowest energy level possible for the electron. And when they do that, they will, this is important, release the energy that they absorbed. So they absorb energy from some outside source. The electrons jump to a higher energy level, and then they release that energy, and the electron jumps back down to the lower energy level. When it emits that energy, it does so in the form of something called a photon. And a photon is the physics word for a packet of energy, a quanta of energy. And photons are quantized. You can't have a photon exist or come out of energy level that's between two energy levels. You know, it could be at n equal 3, it can be at n equal 2, but there's no such thing as n equal 2.5. So energy is quantized when it comes out of atoms, which means it always happens in discrete amounts. So we're going to look at a little PhET simulation of that. And we're going to get to see the hydrogen atom. And, actually, I got it already pulled up here. And we're also going to see all kinds of light energy bombarding this hydrogen atom. So I've got the Bohr model pulled up. I'm shining white light on it. And right now I have my simulation running really slowly. So all that light is showing you energy, different kinds of energy of different frequencies moving up the screen. And here in a second, that just happened. Some of the energy will hit that electron and it will jump to a higher energy level. So let's watch it for just a second. I'm watching that electron. It's going around and around. It's in the n equal 1 energy level. And it got bumped to the n equal 2, 3, 4, to the n equal 5 energy level, that little blue electron. Okay, now it gave off some energy. It dropped back down to n equal 4. Now it gave off some energy. It dropped to n equal 3. Let's see. Drop down back down to n equal 2 or n equal 1. Let's see if it absorbs some energy again. Come on, light. Hit that nucleus or hit that electron. Nothing. Still at n equal 1. Where's the electron going to go next? Come on, come on. Oh, something's headed straight for it. Here it goes. Boom, it hit it. And that electron jumped out to n equal 2. Again, it's not going to stay there. Okay, it's going to just kick out a photon of energy and it drops back down to n equal 1. It just did it. So this just kind of shows you how the electron can jump out to higher energy levels and then drop back to lower energy levels and emit energy. All right, let's go back to our PowerPoint here. It's a really fun simulation. Alrighty, so let's understand what electromagnetic energy is. We're going to need to understand that to understand how we can use light to prove that electrons exist in energy levels, which is what the Bohr Model says. So you might have heard of Roy G. Biv, which is the colors of the visible light spectrum, but actually there's a whole continuous color with all the shades in between. And on page 8 at the bottom, you've got the full electromagnetic spectrum here. Okay, with all the different types. And on the left side, these are considered waves, electromagnetic waves, because they're really long wavelength, which means low frequency, and they like to bounce off of things. So they bounce off of you and buildings or whatever. They're really safe. And then on the other end, you've got the, I'm backwards, sorry. These are the long wavelength waves over here. And then on the other end, you've got the shorter wavelengths, and these tend to travel in straighter lines, and they have a lot more penetrating power. They tend to be a little bit more dangerous, and they're high frequency. And then in the middle, you've got a very narrow part of the spectrum is like right here, 10 to the 6th to 10 to the 7th, that little part right there. That wavelength range is the visible light range, and that's what we can see as human beings. And they've, at the bottom, they kind of broke that out and divided it into the range for the visible colors. So color is linked, the color we see is linked to specific wavelengths of light. Color is linked to wavelength and frequency. So because light can travel as a wave and waves always have frequency, there's kind of a wide range of frequencies in the whole spectrum, but we can't see them all. You know, we can't see radio waves and X-rays and ultraviolet, infrared. We can see color, the visible light spectrum. So we see a color range from a wavelength of 700 nanometers, that's 7 times 10 to the negative 6 nanometers, down to 400 nanometers. So that's 4 times 10 to the negative 6 meters. And then we can see the colors in between, unless you're colorblind. And then you have some other problems. So there's lots of shades in between, and each individual little shade would have a slightly different value for its wavelength and frequency. So let's understand that the sun, a great big ball of energy up there, it gives us energy in the whole continuous electromagnetic spectrum. So it sends out X-rays, visible light, gamma rays, radio waves, believe it or not, and certainly visible light that we see. The sun is constantly bombarding us with all these things, but we don't experience all that on the surface of the planet because our magnetic field and our atmosphere help block and absorb a lot of those kinds of energies. Now, if you've ever seen a rainbow in the sky, that's going to be kind of important to understand that. The electromagnetic spectrum that comes from the sun has colors that we don't see. If you just look at sunlight, you don't see colors. It's called white light, and it's actually made up of all the colors. But it's possible to see the individual colors in the white light if you can get the white light to bend, because each color will bend at a slightly different angle. So if you've ever seen a rainbow in the sky, you are looking at the spectrum of color contained in white light, and it's created through the bending of that white light through water drops. You can get the same effect with a prism. right? If you've ever looked at light shining through a prism and you get that white light to bend, every color bends at a little bit different angle, and that stretches out all the different colors. And that's where we kind of came up with the Roy G. Biv thing, which is the colors. Now, this is a phenomena, getting light to bend at different angles. That's called diffraction in physics. So what we're going to use in our class is something called a diffraction grating, which is a little film that has scratches on it, and the light passes through the scratches, and as it hits the edges of the scratches, it bends, and each color of light will bend at a different angle. And the fun thing with diffraction gratings is you don't just see one rainbow, okay? You'll see a rainbow on the left and a rainbow on the right, and then that repeats right outside those rainbows. You'll see a repeating rainbow pattern. That's called the second order. And then you'll see another one. That's called the third order. They get a little fainter as they go out. Okay, so we're going to use diffraction grating. So each repeating, you have a rainbow on the right, a rainbow on the left that's reversed, and then you'll have repeating order right outside of that. So you'll see that when we do the diffraction lab. Okay, so what if it's not white light? Okay, if it's white light, right, we see the full spectrum. What if we diffract, but what if we diffract light that's not white light? What if it doesn't have all of the colors in it? Well, you can still diffract it into a spectrum. You're just not going to see the full rainbow. You're only going to see part of the rainbow. So what if our light comes from something like hydrogen? What if we can get hydrogen gas to glow and emit light, and we send it through a diffraction grating? Well, this creates something called an emission spectrum. And the emission spectrum from hydrogen looks like this. It's got 4 lines. You're going to see a very distinct red line. You'll see a very distinct kind of purple violet line on the end. The green and the blue lines are a little bit harder to tell. The green is more like a blue-green, and the blue is kind of a brightish green color. So the colors aren't quite perfect here, but you will see those 4 spectral lines. And let me move my picture of me so you can see the wavelengths. Okay, so the red line, the longest wavelength spectral line, is 656, and then you have a 486, a 434, and a 410, and those are the spectral lines we'll be observing using hydrogen gas and our diffraction gratings. So how are looking at lines in a diffraction grating proof of energy levels? Well, again, if you look at your Bohr model here, it turns out that the colors and lines that you see, so for the visible light series that we see 4 lines, right? And I just told you their wavelengths. Here they are again. Okay, here's your 656, that would be your red, and so on. They correspond to movements of electrons, and we call these transitions. So this one would be a transition between the 3rd energy level and the 2nd energy level, n equal 3 to n equal 2. And if I follow that line down, I can see that the energy of the photon that it's emitted is going to emit a visible light color of wavelength 656 nanometers. When you have a sample of hydrogen, you have so many hydrogen atoms in that sample that they're all doing something different, and you can see all 4 lines. It's pretty cool. So we're going to do a couple practice problems to help you figure out how to read this chart. Now, if you get into a more advanced physics class, okay, or advanced chemistry class, you'll be calculating how the energy levels of the electrons and their positions and possible locations relates to the spectral lines in a little bit different way. You're going to use Planck's constant. You're going to use this really cool equation that says that energy is equal to Planck's constant times frequency. You'll do a speed of light calculation where the speed of light is equal to frequency times wavelength. Pretty cool stuff. But we're going to skip all that. Thank goodness. We do not have to prove this quantitatively. We just have to be able to correspond the transitions in the energy levels for the electron to the wavelength of the spectral line that is created by that photon of light that's emitted when it drops to a lower energy level. So let's look at some example questions. Here's one where we have a hydrogen atom. It's got electrons. The electrons transition, it says transition from n equal 5 to n equal 2. And we want to figure out what wavelength of photon would be emitted. So when it drops, remember when the electron drops to a lower energy level, it has to lose that electron or that energy that it had absorbed. And it does it by ejecting a photon. And we want to figure out how much energy does that photon have. And then I want to figure out number 2, I want to figure out what type. Would this be visible light? Would it be infrared? Would it be ultraviolet? I don't think it could be anything like X-rays because they haven't given me that as a choice, right? It has to be something coming off of a Bohr model. So it's got to be either in the infrared range, the visible light range, or the ultraviolet range. All right, so let's get into that. So question number 1, it says the atom has an electron that transitions from n equal 5 to n equal 2. So look very closely. Find the n equal 5 ring, find the n equal 2 ring, follow your finger around. Ignore all of these other lines. There's so much information packed into here, okay? You got to eliminate things. So you just want to find the dot, the electron dot here, that corresponds to a movement between n equal 5 and n equal 2. So start here at n equal 5, follow your finger around. Okay, find a dot that starts at n equal 5. Here's one. And then say, does it drop to n equal 2? And I see right here, yes, it does. So eliminate, don't look at any other lines except for this line, n equal 5 to n equal 2. That's the only one you want to look at. Okay, and then follow your finger down. Follow, 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 follow. Okay, and I see down here this number, 434. 434, that tells me the wavelength in nanometers. That is the wavelength of the photon that is emitted when that electron drops to that lower energy level. So that answers the first part of my question. Now, I want to do this answer in meters because they said, what is a wavelength in meters? So when I need to convert nanometers to meters, we just jump our decimal point left 9 times. So that gives me 0.000000434, 6 O's. And that's, of course, horrible to write. So we'll put that into scientific notation, and we get 4.34 times 10 to the negative 7. And hint, hint, y'all, just move the decimal 2 times and add the times 10 to the negative 7. And that converts it to meters for you. Okay, so the first part of my answer is the wavelength of the photon that is emitted when the electron transitions from n equal 5 to n equal 2 is a wavelength of 4.34 times 10 to the negative 7 meters. Now, second part is, what type of energy would this be? Well, I've kind of already figured out, based on what they gave me here, that 434 is in the visible range, okay? But I can also look here, because it's 10 to the negative 7, right? 10 to the negative 7. So if I look here on at the top, it kind of gives me a little idea of what ranges the wavelengths would be. And if I kind of follow my finger down, I see that that's visible light. So I will be able to see that. Okay, that's visible light. Then they'd say, if it is visible light, tell us the corresponding color. Okay, so for that, you've got to kind of look down here at the bottom where it blows up the visible light colors. Okay, blue is 4.9 to 4.2. So 4.34 would fall in that range. It's very close to violet. It would be like right here. So it'll be a blue color. All right, and that's an example of how to use your Bohr model and figure out the corresponding wavelength and determine what type of electromagnetic energy it is. And then if it's visible light, you say what color it is. Okay, so those are my final answers there. 4.34 times 10 to the negative 7 meters and visible light blue. Let's look at another example. Let's go backwards this time. So what if I know the wavelength and I want to figure out what the energy level transitions would be? So they're giving me a wavelength of 1282. So let me find 1282. Right here it is, 1282. And I can see if I look down here, IR. IR means infrared. So right there, I know I won't be able to see that light. It's outside of the visible range. Okay, but here is its wavelength. And then if I look up, I can see what energy level it starts at, and I can see what energy level it transitions to. So it looks to me like it is starting at n equal 5, and it's transitioning down to n equal 3. So it's a 5 to 3 transition there. And by the way, if you don't have visible light, these actually have names. They don't say them on here, but these spectral lines that would be emitted in the infrared range, those are called the Passion series spectral lines. The visible ones are called the Balmer series. There's 4 of those. And then the ultraviolet is called the Lyman series, and that's just named after the people that discovered them. Have to give them credit since they made amazing discoveries. Okay, last example. So let's look at the Lyman series. This is the ultraviolet series, and there are 3 lines, and we want to just list each wavelength and convert it to meters, and then give the corresponding transition that the electron has to make to create those spectral lines. Okay, so first I'm going to say just 122, 103, and 97. All of that would be nanometers. And again, you want to convert that into meters. And I actually have a typo in here. That should be 7. So jump your decimal left 3 times, or 9 times, excuse me, and then move it back to convert to scientific notation. That's very complicated. So quick way to do it is just move your decimal left 2 times and then add times 10 to the negative 7. That's how I always remember it. That's how you convert nanometers to meters for this. And then see what it corresponds to. So if I follow the 122 line up, let me find my 122 line. Where are you? There we are. We follow it up. Then I can see it starts at n equal 2. And then it transitions to n equal 1. So n equal 2 to n equal 1 is that transition. And then the next spectral line, the 103 spectral line, starts here at n equal 3, and it transitions to n equal 1. So n equal 3 to n equal 1 for the 103 nanometer line. And then the 97 nanometer line starts here at n equal 4, and it transitions down to n equal 1. So n equal 4 to n equal 1. Alrighty, so there's 3 examples of using transitions in electron energy levels for the Bohr model and figuring out the corresponding wavelengths of spectral lines that are created in a diffraction. So just a few comments here on detecting electromagnetic waves and radiation. We can only see spectral lines that transition down to the n equal 2 energy level. So if it's coming from n equal 3 to n equal 2, n equal 4 to n equal 2, n equal 5 to n equal 2, it has to end up on n equal 2, and we're able to see it. That's because the size of our eyes, okay, the way our eyes are anatomically oriented and created, can only see wavelengths about the size of a virus. Okay, so the wavelength of the light coming in is like this, and the wavelength itself, the height of the wavelength itself is only about the size of a virus. So we're not talking about big, huge wavelengths here. We cannot see ultraviolet, infrared, X-rays, radio waves, but that doesn't mean they don't exist. In fact, they're all around us, and there's lots of things that we use every day that can detect and create this type of electromagnetic waves and radiation. Wi-Fi is a form of electromagnetic radiation. It's just a really long wavelength, and so it's very bouncy. It doesn't penetrate you. It just kind of bounces around, bounces off of you. So it's pretty harmless to us. Satellite receivers, same thing. The signal will just bounce off of things, which is why sometimes if you turn on your radio and you're driving up in the mountains, you can get some really weird bounce signals from radio stations that are really far away. Depends on the weather. Also, electromagnetic waves are broadcast all around us. So big cell phone towers, those things are blasting out electromagnetic waves. Broadcast towers, blasting out electromagnetic waves. Microwaves contain electromagnetic waves. So electromagnetic waves are all around us. We just have to be careful. Some of them are harmful, and that is where we get into electromagnetic radiation. So anything longer wavelength, lower frequency than visible light, anything to the left here, is going to be considered a wave. Longer wavelength means lower frequency, and they tend to be pretty safe. They're not real penetrating. But when we go higher, we have shorter wavelengths. They become more like arrows. Okay, shorter wavelength. They're not doing this. They're more straight. And so they can be a lot more penetrating. And the higher the frequency, the shorter the wavelength up here, like the gammas, they can actually penetrate through humans and ping some of your chromosomes out and cause diseases and things like that. So we have to be careful with the radiation side of that electromagnetic table. So this has been a presentation on the emission spectrum. I hope you think it's pretty cool that we can prove that energy levels exist just by looking at spectral lines created from the diffraction of a gas like hydrogen. So thanks for joining me. Have a good one.